Understanding Physics, 3 volumes in 1, by Isaac Asimov. Recorded, edited, and produced by JohnLothe. Chapter 2, Falling Bodies. Inclined Planes. Galileo's chief difficulty was the matter of timekeeping. He had no clock worthy of the name, so he had to improvise methods. For instance, he used a container with a small hole at the bottom, out of which water dripped into a pan at, presumably, a constant rate. The weight of water, caught in this fashion, between 2 events was a measure of the time that had elapsed. This would certainly not do for bodies in free fall, that is, falling downward without interference. A free fall from any reasonable height is over too soon, and the amount of water caught during the time of fall is too small to make time measurements even approximately accurate. Galileo therefore decided to use an inclined plane. A smooth ball will roll down a smooth groove on such an inclined plane at a manifestly lower speed than it would move if it were dropping freely. Furthermore, if the inclined plane is slanted less and less sharply to the horizontal, the ball rolls less and less rapidly. With the plane made precisely horizontal, the ball will not roll at all, at least not from a standing start. By this method, one can slow the rate of fall to the point where even crude time-measuring devices can yield useful results. One might raise the point as to whether motion down an inclined plane can give results that can fairly be applied to free fall. It seems reasonable to suppose that it can. If something is true for every angle at which the inclined plane is pitched, it should be true for free fall as well. For free fall can be looked upon as a matter of rolling down an inclined plane that has been maximally tipped, that is, one that makes an angle of 90 degrees with the horizontal. For instance, it can be easily shown that relatively heavy balls of different weights would roll down a particularly inclined plane at the same rate. This would hold true for any angle at which the inclined plane was tipped. If the plane were tipped more sharply, the balls would roll more rapidly, but all the balls would increase their rate of movement similarly. In the end, all would cover the same distance in the same time. It is fair to conclude from that alone that freely falling bodies will fall through equal distances in equal times, regardless of their weight. In other words, a heavy body will not fall more rapidly than a light body, despite the Aristotelian view. There is a well-known story that Galileo proved this when he dropped 2 objects of different weight off the Leaning Tower of Pisa, and they hit the ground in a simultaneous thump. Unfortunately, this is just a story. Historians are quite certain that Galileo never conducted such an experiment, but that a Dutch scientist, Simon Stevinus, 1548 to 1620, did something of the sort a few years before Galileo's experiments. In the cool world of science, however, careful and exhaustive experiments such as those of Galileo with inclined planes sometimes count for more than single sensational demonstrations. Yet can we really dispose of the Aristotelian view so easily? The observed equal rate of travel on the part of balls rolling down an inclined plane cannot be disputed, but on the other hand, neither is it possible to dispute the fact that a soap bubble falls far more slowly than a ping-pong ball of the same size, and that the ping-pong ball falls rather more slowly than a solid wooden ball of the same size. We have an explanation for this, however. Objects do not fall through nothing. They fall through air, and they must push the air aside, so to speak, in order to fall. We might take the viewpoint that to push the air aside consumes time. A heavy body pressing down hard presses the light air to one side with no trouble and loses virtually no time. It doesn't matter whether the body is 1 pound or 100 pounds. The 1 pound weight experiences so little trouble in pushing the air to one side that the 100 pound weight can scarcely improve on it. Both weights, therefore, fall through equal distances in equal times. A distinctly light body, such as a ping-pong ball, would press down so softly that it would experience considerable trouble in pushing the air out of the way, and it would fall slowly. A soap bubble, for the same reason, would scarcely fall at all. Can this use of air resistance as an explanation be considered valid? Or is it just something concocted to explain the failure of Galileo's generalization to hold in the real world? Fortunately, the matter can be checked. First, suppose that of two objects of equal weight, one is spherical and compact, while the other is wide and flat. The wide, flat object will make contact with air over a broader front and have to push more air out of the way in order to fall. It will therefore experience more air resistance than the spherical compact one, and will fall more slowly, even though the two bodies are of equal weight. This turns out to be so when tested. In fact, if a piece of paper is crumpled into a pellet, it falls more quickly because it suffers less air resistance. I referred to this experiment on page 9 as being one the Greeks might easily have performed, and from which they might have discovered that there must be something wrong with the Aristotelian view of motion. An even more unmistakable test would be to get rid of air and allow bodies to fall through a vacuum, with no resistance to speak of. All bodies, however light or heavy they might be, ought to fall through equal distances in equal times. Galileo was convinced this would be so, but in his time there was no way of creating a vacuum to test the matter. In later years, when vacuums could be produced, the experiment of causing a feather and a lump of lead to fall together in a vacuum, and noting the fact that both covered an equal distance in an equal time, became commonplace. Air resistance is therefore real and not just a face-saving device. Of course, this raises the question of whether one is justified for the sake of enunciating a simple rule in describing the universe in non-real terms. Galileo's rule that all objects of whatever weight fell through equal distances in equal times could be expressed in very simple mathematical form. The rule is true, however, only in a perfect vacuum, which, as a matter of fact, does not exist. Even the best vacuums we can create, even the vacuum of interstellar space, are not perfect. On the other hand, Aristotle's view that heavier objects fall more rapidly than light ones is true, at least to a certain extent, in the real world. Footnote. Actually, there is a small difference. This does not show up in falls of reasonable length, but would become visible if both weights were dropped from an airplane. In such case, the lighter weight would be held up a bit and lag behind a little. However, it cannot be reduced to as simple a mathematical statement, for the rate of fall of particular bodies depends not only upon their weight, but also upon their shapes. One might suppose that reality must be held to at all costs. However, though that may be the most moral thing to do, it is not necessarily the most useful thing to do. The Greeks themselves chose the ideal over the real in their geometry, and demonstrated very well that far more could be achieved by consideration of abstract line and form than by a study of the real lines and form of the world. The greater understanding achieved through abstraction could be applied most usefully to the very reality that was ignored in the process of gaining knowledge. Nearly 4 centuries of experience since Galileo's time has shown that it is frequently useful to depart from the real and to construct a model of the system being studied. Some of the complications are stripped away, so a simple and generalized mathematical structure can be built up out of what is left. Once that is done, the complicating factors can be restored one by one, and the relationship subtly modified. To try to achieve the complexities of reality at one bound without working through a simplified model first is so difficult that it is virtually never attempted, and we can feel certain would not succeed if it were attempted. It is useless then to try to judge whether Galileo's views are true and Aristotle's false, or vice versa. As far as rates of fall are concerned, there are observations that back one view and other observations that back the other. What we can say, however, as strongly as possible, is that Galileo's views of motion turned out to explain many more observations in a far simpler manner than did Aristotle's views. The Galilean view was, therefore, far more useful. This was recognized not too long after Galileo's experiments were described and Aristotelian physics collapsed. Acceleration. If we were to measure the distance traversed by a body rolling down an inclined plane, we would find that the body would cover greater and greater distances in successive equal time intervals. Thus, a body might roll a distance of 2 feet in the first second. In the next second, it would roll 6 feet, for a total distance of 8 feet. In the third second, it would roll 10 feet, for a total distance of 18 feet. In the fourth second, it would roll 14 feet, for a total distance of 32 feet. Clearly, the ball is rolling more and more rapidly with time. This, in itself, represents no break with Aristotelian physics, for Aristotle's theories said nothing about the manner in which the velocity of a falling body changed with time. In fact, this increase in velocity might be squared with the Aristotelian view. For one might say that as a body approached its natural place, its eagerness to get there heightened, so its velocity would naturally increase. However, the importance of Galileo's technique was just this. He took up the matter of change of speed, not in a qualitative way, but in a quantitative way. It is not enough to simply say, velocity increases with time. One must say, if possible, by just how much it increases and work out the precise interrelationship of velocity and time. For instance, if a ball rolls 2 feet in 1 second, 8 feet in 2 seconds, 18 feet in 3 seconds, and 32 feet in 4 seconds, it would appear that there was a relationship between the total distance covered and the square of the time elapsed. Thus 2 is equal to 2 times 1 squared. 8 is equal to 2 times 2 squared, and 18 is equal to 2 times 3 squared, and 32 is equal to 2 times 4 squared. We can express this relationship by saying that the total distance traversed by a ball rolling down an inclined plane or by an object in free fall after starting from rest is directly proportional to the square of the time elapsed. Footnote: when we say that A is directly proportional to B, we mean that as B increases, A increases as well. Sometimes a relationship is such that as B increases, A decreases. For instance, as the price of an object increases, the number of sales may decrease. We then say that A is inversely proportional to B. Physics has adopted this emphasis on exact measurement that Galileo introduced, and other fields of science have done likewise, wherever this has been possible. The fact that chemists and biologists have not adopted the mathematical attitude as thoroughly as physicists is no sign that chemists and biologists are less intelligent or less precise than physicists. Actually, This has come about because the systems studied by physicists are simpler than those studied by chemists and biologists, and are more easily idealized to the point where they can be expressed in simple mathematical form. Now consider the ball rolling 2 feet in 1 second. Its average velocity, that is distance covered in unit time, during that 1 second interval is 2 feet divided by 1 second. It is easy to divide 2 by 1, but it is important to remember that we must divide the units as well, the feet, by this second. We can express this division of units in the usual fashion by means of a fraction. In other words, 2 feet divided by 1 second can be expressed as 2 feet over 1 second, or 2 feet/second. This can be abbreviated as 2ft/sec, and is usually read as 2 feet per second. It is important not to let the use of per blind us to the fact that we are in effect dealing with a fraction. Its numerator and denominator are units rather than numbers, but the fractional quality remains nevertheless. But to return to the rolling ball, in 1 second it covers 2 feet, for an average velocity of 2 feet per 1 second. In 2 seconds it covers 8 feet, for an average velocity over the entire interval of 4 feet per second. In 3 seconds it covers 18 feet, for an average velocity over the entire interval of 6 feet per 1 second. And you can see for yourself the average velocity for the first 4 seconds is 8 feet per second. The average velocity, all told, is in direct proportion to the time elapsed. Here, however, we are dealing with average velocities. What is the velocity of a rolling ball at a particular moment? Consider the first second of time. During that second, the ball has been rolling at an average velocity of 2 feet per second. It began that first second of time at a slower velocity. In fact, since it started at rest, the velocity at the beginning, after 0 seconds, in other words, was 0 feet per second. To get the average up to 2 feet per second, the ball must reach correspondingly higher velocities in the second half of the time interval. If we assume that the velocity is rising smoothly with time, it follows that if the velocity at the beginning of the time interval was 2 feet per second, less than average, then at the end of the time interval, after 1 second, it should be 2 feet per second more than average, or 4 feet per second. If we follow the same line of reasoning for the average velocities in the first 2 seconds, in the first 3 seconds, and so on, we come to the following conclusions. At 0 seconds, the velocity is 0 feet per second. At 1 second, the velocity, at that moment, is 4 feet per second. At 2 seconds, the velocity is 8 feet per second. At 3 seconds, the velocity is 12 feet per second. At 4 seconds, the velocity is 16 feet per second, and so on. Notice that after each second, the velocity is increased by exactly 4 feet per second. Such a change in velocity with time is called an acceleration, from the Latin words meaning to add speed. To determine the value of the acceleration, we must divide the gain in velocity during a particular time interval by that time interval. For instance, at 1 second, the velocity was 4 feet per second, while at 4 seconds it was 16 feet per second. Over a 3-second interval, the velocity increased by 12 feet per second. The acceleration then is 12 feet per second, divided by 3 seconds. Notice particularly that it is not 12 feet per second divided by 3. Where units are involved, they must be included in any mathematical manipulation. Here you are dividing by 3 seconds and not by 3. In dividing 12 feet per second by 3 seconds, we get an answer in which the units as well as the numbers are subjected to the division. In other words, 4 feet per second divided by second. This can be written 4ft/SEC/SEC and is read as 4 feet per second per second. Then again, in algebraic manipulation, A/B divided by B is equal to A/B multiplied by 1/B, and the final result is A/B squared. Treating unit fractions in the same manner can be written 4ft/SEC squared and read 4 feet per second squared. You can see that in the case just given, for whatever time interval you work out the acceleration, the answer is always the same, 4 feet per second squared. For inclined planes tipped to a greater or lesser extent, the acceleration would be different, but it would remain constant for any one given inclined plane through all time intervals. This makes it possible for us to express Galileo's discovery about falling bodies in simpler and neater fashion. To say that all bodies cover equal distances in equal times is true. However, it is not saying enough, for it doesn't tell us whether bodies fall at uniform velocities, at steadily increasing velocities, or at velocities that change erratically. Again, if we say that all bodies fall at equal velocities, we are not saying anything about how those velocities may change with time. What we can say now is that all bodies, regardless of weight, neglecting air resistance, roll down inclined planes or fall freely at equal and constant accelerations. When this is true, it follows quite inevitably that two falling bodies cover the same distance in the same time, and that at any given moment they are falling with the same velocity, assuming both started falling at the same time. It also tells us that the velocity increases with time and at a constant rate. Such relationships become useful if we introduce mathematical symbols to express our meaning. In doing so, we introduce nothing essentially new. We would be saying in mathematical symbols exactly what we have been trying to say in words, but more briefly and more generally. Mathematics is a shorthand language in which each symbol has a precise and agreed-upon meaning. Once the language is learned, we find that it is only a form of English after all. For instance, we have just been considering the case of an acceleration from rest of 4 feet per second squared. This means that at the end of 1 second, the velocity is 4 feet per second. At the end of 2 seconds, it is 8 feet per second. At the end of the 3 seconds, it is 12 feet per second, and so on. In short, the velocity is equal to the acceleration multiplied by the time. If we let v stand as a symbol for velocity and t for time, we can say that in this case, v is equal to 4t. But the actual acceleration depends on the angle at which the inclined plane is tipped. If the plane is made steeper, the acceleration increases. If it is made less steep, the acceleration decreases. For any given plane, the acceleration is constant, but the particular value of the constant can vary greatly from plane to plane. Let us not, therefore, commit ourselves to a particular numerical value for acceleration, but let this acceleration be represented by a. We can then say v equals at. Equation 2-1. It is important to remember that included in such equations in physics are units as well as numerals. Thus a, in equation 2-1, does not represent a number merely, say 4, but a number and its units, 4 feet per second squared. The unit being appropriate for acceleration. Again, t for time represents a number and its units, 3 seconds, let us say. In evaluating at, then, we multiply 4 feet per second squared by 3 seconds, multiplying the units as well as the numerals, treating the units as though they were fractions. In other words, as though we were to multiply a per b squared by b. The product is 12 feet per second, thus multiplying acceleration, a, by time, t, does indeed give us velocity, v, since the units we obtain, feet per second, are appropriate to velocity. In any equation in physics, the units on either side of the equals sign must balance after all necessary algebraic manipulation is concluded. If this balance is not obtained, the equation does not correspond to reality and cannot be correct. If the units of one symbol are not known, they can be determined by deciding just what kind of unit is needed to balance the equation. This is sometimes called dimensional analysis. With that out of the way, let us consider a ball starting from rest and rolling down an inclined plane for t seconds. Since the ball starts at rest, its velocity at the beginning of the time interval is 0 feet per second. According to equation 2.1, at the end of the interval, at time t, its velocity v is a per t, or feet per second. To get the average velocity during this interval of smoothly increasing velocity, we take the sum of the original and final velocity, 0 plus a per t, and divide by 2. The average velocity during the time interval is therefore a per t divided by 2. The distance, d, traversed in that time must be the average velocity multiplied by the time, a per t divided by 2 times t. We therefore conclude that d equals a per t squared divided by 2. Equation 2.2. I will not attempt to check the dimensions for every equation presented, but let's do it for this one. The units of acceleration, a, are feet per second squared, and the units of time, t, are seconds. Therefore, the units of a per t squared are feet per second squared times second, which works out to feet per second squared divided by second squared, or simply feet. Dividing acceleration per time squared by 2 does not alter the situation, for in this case 2 is a pure number. That is, it lacks units. Thus, if you divide a foot rule in 2, each half has a length of 12 inches divided by 2, or 6 inches. The unit is not affected. Thus, the units of acceleration per time squared divided by 2 are feet, an appropriate unit for distance, d. Free fall. As I said earlier, the value of the acceleration, a, of a ball rolling down an inclined plane varies according to the steepness of the plane. The steeper the plane, the greater the value of acceleration. Experimentation will show that for a given inclined plane, the value of acceleration is in direct proportion to the ratio of the height of the raised end of the plane to the length of the plane. If you represent the height of the raised end of the plane by h and the length of the plane by l, you can express the previous sentence in mathematical symbols as a, 2 lowercase c's pushed up against one another, h/l, where the aforementioned symbol of 2 lowercase c's pushed up against one another means is directly proportional to. In such a direct proportion, the value of the expression on one side changes in perfect correspondence with the value of the expression on the other. If height and length is doubled, acceleration is doubled. If height and length is halved, acceleration is halved. If height and length is multiplied by 2.529. Acceleration is multiplied by 2.529. This is what is meant by direct proportionality. But suppose that for a particular value of acceleration, the value of height and length happens to be just a third as large. If the value of acceleration is changed in any particular way, the value of height and length is changed in a precisely corresponding way. So it is still 1/3 the value of acceleration. In this particular case, then, acceleration is 3 times as large as height and length, not for any one set of values, but for all values. This is a general rule. However, one factor, x, is directly proportional to another factor, y. We can always change the relationship into an equality by finding some appropriate constant value, usually called the proportionality constant, by which to multiply y. Ordinarily, we do not know the precise value of the proportionality constant to begin with, so it is signified by some symbol. This symbol is very often K for constant, using the German spelling. Therefore, we can say that if x is directly proportional to y, then x equals ky. It is not absolutely necessary to use k as the symbol for the proportionality constant. Thus, the velocity of a ball rolling from rest is directly proportional to the time during which it has been rolling, and the distance it traverses is directly proportional to the square of that time. Therefore, velocity is directly proportional to time, and distance is directly proportional to time squared. In the first case, however, we have the special name acceleration for the proportionality constant, so we symbolize it by a, while in the second case, the relationship to acceleration is such that we symbolize the proportionality constant as acceleration divided by 2. Therefore, velocity equals acceleration times time, and distance equals acceleration times time squared divided by 2. The relationship to acceleration is such that we symbolize the proportionality constant as acceleration divided by 2. Therefore, velocity equals acceleration times time, and distance equals acceleration times time squared divided by 2. In the case now under discussion, where the value of the acceleration, a, is directly proportional to height divided by length, it will prove convenient to symbolize the proportionality constant by the letter g. We can therefore say a equals g times height divided by length. Equation 2-3. The quantities, height and length, are both measured in feet. In dividing height by length, feet are divided by feet, and the units cancel. The result is that the ratio, height divided by length, is a pure number and possesses no units. But the units of acceleration, a, are feet divided by seconds squared. In order to keep the units in balance in equation 2-3, it is therefore necessary that the units of g also be feet divided by seconds squared, since height divided by length can contribute nothing in the way of units. We can conclude, then, that the proportionality constant in equation 2-3 has the units of acceleration and therefore must represent an acceleration. We can see what this means if we consider that the steeper we make a particular inclined plane, the greater the height of its raised in from the ground, that is, the greater the value of h. The length of the inclined plane, L, does not change, of course. Finally, when the plane is made perfectly vertical, the height of the raised end is equal to the full length of the plane, so that h equals L, and height divided by length equals 1. A ball rolling down a perfectly vertical inclined plane is actually in free fall. Therefore, in free fall, height divided by length becomes 1, and equation 2-3 becomes acceleration equals g. Equation 2-4. This shows us that g is not only an acceleration, but is the particular acceleration undergone by a body in free fall. The tendency of a body to have weight and fall toward the earth is the result of a property called gravity, from the Latin word for weighty. And the symbol g is used because it is the abbreviation of gravity. If the actual acceleration of a body rolling down any particular inclined plane is measured, then the value of g can be obtained. Equation 2-3 can be rearranged to yield g equals a times L divided by h, or gravity equals acceleration times length divided by height. For a particular inclined plane, the length L and height h of the raised in are easily measured, and with acceleration a known, g, gravity, can be determined at once. Its value turns out to be equal to 32 feet per second squared, at least at sea level. Now, so far, for the sake of familiarity, I have made use of feet as a measure of distance. This is one of the common units of distance used in the United States and Great Britain, and we are accustomed to it. However, scientists all over the world use the metric system of measure, and we have gotten far enough into the subject, I think, to be able to join them in this. The value of the metric system is that its various units possess simple and logical relationships among themselves. For instance, in the common system, 1 mile is equal to 1,760 yards. 1 yard is equal to 3 feet, and 1 foot is equal to 12 inches. Converting one unit to another is always a chore. In the metric system, the unit of distance is the meter. Other units of distance are always obtained by multiplying the meter by 10 or a multiple of 10. Thanks to our system of writing numbers, this means that conversions of one unit to another within the metric system can be carried out by mere shifts of a decimal point. Furthermore, standardized prefixes are used with set meaning. The prefix deci always implies 1/10 of a standard unit, so a decimeter is 1/10 of a meter. The prefix hecto also implies 100 times a standard unit, so a hectometer is 100 meters, and so it is for other prefixes as well. The meter itself is 39.37 inches long. This makes it the equivalent roughly of 1.09 yards, or 3.28 feet. Two other metric units commonly used in physics are the centimeter and the kilometer. The prefix centi implies 1/100th of a standard unit, so a centimeter is 1/100th of a meter. It is equivalent to 0.3937 inches, or approximately 2/5 of an inch. The prefix kilo implies 1,000 times the standard unit, so a kilometer is equal to 1,000 meters, or 100,000 centimeters. The kilometer is 39,370 inches long, which makes it just about 5/8 of a mile. The abbreviations ordinarily used for meter, centimeter, and kilometer are m, cm, and km, respectively. Seconds, as a basic unit of time, are used in the metric system as well as in the common system. Therefore, if we want to express acceleration in metric units, we can use meters per second, or meters per second squared for the purpose. Since 3.28 feet equal 1 meter, we divide 32 feet per second squared by 3.28 and find that in metric units, the value of g is 9.8 meters per second squared. Once again, consider the importance of units. It is improper and incorrect to say that the value of g is 32, or the value of g is 9.8. The number by itself has no meaning in this connection. One must say either 32 feet per second squared or 9.8 meter per second squared. These last two values are absolutely equivalent. The numerical portions of the expression may be different, taken by themselves, but with the units added, they are identical values. One is by no means more true or more accurate than the other. The expression in metric units is merely more useful. We must know at all times which units are being used. In free fall, acceleration is equal to gravity. So equation 2-1 can be written v equals 32 times t if we are using common units, and v equals 9.8 times t if we are using metric units. In the shorthand of equations, the units are not included, so there is always the chance of confusion. If you try to use common units with the equation v equals 9.8 times t, or metric units with the equation v equals 32 times t, you will end up with results that do not correspond to reality. For that reason, the rules of procedure must be made perfectly plain. In this book, for instance, it will be taken for granted henceforward that the metric system will be used at all times, except where I specifically say otherwise. Therefore, we can say that for bodies in free fall from a starting position at rest, v equals 9.8 times t. In the same way, for such a body, equation 2-2 becomes d equals g times t squared divided by 2, or d equals 4.9 times t squared. Equation 2-5. In the same way, for such a body, equation 2-2 becomes d equals g times t squared divided by 2, or d equals 4.9 times t squared. Equation 2-6. At the end of 1 second, then, a falling body has dropped 4.9 meter and is falling at a velocity of 9.8 meters per second. At the end of 2 seconds, it has fallen through a distance of 19.6 meters and is falling at a velocity of 19.6 meters per second. At the end of the 3 seconds, it has fallen through a distance of 44.1 meter and is falling at a velocity of 29.4 meters per second, and so on. Footnote: since this book is not intended as a formal text, I'm not presenting you with problems to be solved. I hope, nevertheless, that you have had enough experience with algebra to see that equations in physics not only present relationships in brief and convenient form, but also make it particularly convenient to solve problems. That is, to find the value of a particular symbol when the values of the other symbols in the equation are known and can be determined. If you enjoyed this recording, you can find more and support the production of these works at my website, JohnLothe.wordpress.com. That's www.JohnLothe.wordpress.com. Thanks for having a look and a listen. Your friend, John Lothe.